Hope you guys are doing well. So, continuing our journey with authentication. Now, we are going to study the fundamentals of authentic of cryptography, right? I mean, how authentication is going to be performed. So, and like, what are the different types of encryption and decryption methods that we can use? So, like in last we learned why do we need authentication, right? And now we'll see some fundamentals. In the previous chapter we said that web architectures are okay. Just let me check once if everything is running on Twitch, because sometimes Twitch does not work as expected it to work. So just making sure that it's okay. Video, yeah. Let's go to my. Okay, so yeah, a fundamentals of cryptography. In previous chapter, we said web architectures are essentially unsecured, right? For any practical business application, maybe not in clear terms, but quite close. We learned that the internet traffic travels to every device in the network. It does not have any privacy or protection. Now it does, so anyone can tap the wire and view all the exchange of traffic in the network. Now we mentioned that HTTP session management will happen with cookies. The cookies flow over the wire like other network traffic, hence anyone tapping can see them. Development in cryptography in 70s and 90s led to finding some principles that can address these issues and while keeping the underlying architecture simple. Fortunately, cryptography is a common complex subject. Unfortunately, cryptography it's a bit complex, so because it requires some high level mathematician and requires some study understanding. So we will try to understand why do we go for cryptography, right? Now, security by obscurity. Now, think of a box where you're hiding a secret document. You have two options. First is hide that. Okay, so now, so let's assume that this is our box, right? And then to open this box, I need a key, right? So there are two possible things here I can do. Uh, First is basically make this so like this is like assume like you need to input in a code here, right? You're going to input a code. So the first thing that I can do is make this code available to only limited number of people. The second thing what I can do is okay, now the first system will be security system by obscurity, and so and then the other thing is basically making that the combination here is foolproof, right? So that no one else um can open the lock, right? So this is nothing but this method of only limiting the number of users who can access my code is basically called as obscurity. The security by obscurity is not reliable as it's always from, yeah. So I mean it may depend, right, from person to person. So now if these two persons are ready and or are like talking terms, so then he might not share the key with others, right? What if these two persons get in a fight? Now when that happens there are tendency that these two persons can leak out the key, right? So that is not a very good way. Now there is no test or strength of security systems such as okay, and now for example, okay, and okay, so there is no way to test the security system such as system may not have been subjected to formal crypto analysis. It is not seal able to find a foolproof secure algorithm for every user or implementation. we are interested in the second kind of. So our goal is basically to make a password foolproof. So what are we going to do is making a foolproof password. Now, algorithms of cryptography should be known to everyone. Security of the system only relies on a key of binary data experts who have analyzed the algorithms to ensure that they cannot be intruded on infinite time and effort when keys are not available. Hence, the creator does not get any. Okay, so now here the problem or the advantage is this. Okay, so I mean, what are the issues here? First is the person who has created the lock already knows how to access the lock. Okay. Uh, because the creator of or the person who has created the system knows, right, how the lock will be created and so on. um yeah, so basically the creator of the lock creator has access to the codes, right? So the creator has access to all the codes. So this is not a very foolproof. What we are doing is we are trying to make this foolproof. We are focusing on this where we developed a foolproof password in such a way. Okay, so I mean, what is going to happen is so like uh, the person creates the password, and then suppose I'm the user or I have created this token. Yeah, so what is going to happen is um basically what we are trying to do is, suppose this is like a vault, and inside that we are going to store our documents, and this is the lock for the vault. So there are two things that we can do here. Either one of them is basically you have a very, so this is the lock, and one of them is basically this lock should be as secure as either you hide the lock, like hide what the key is, or second is basically you kind of give access to certain restricted number of people. Now what is going to happen is these restricted people can leak out the keys, right? So we are not interested in this system. Instead we want to design a foolproof system, right, so that the keys are hidden. Now for this we are going to use different types of methods, right? First is message. So then okay, now message, not for the, okay, there are different types of mechanisms, right? Okay, now first thing that we need to study is about message consistency. Suppose these are two people. So there are certain topics that we need to cover, right? Okay, so first thing is basically we are going to talk about message consistency, right? And let us understand what do we mean by this phrase. Now, so suppose there are two people, right, and they want to communicate over the internet. So, okay, let's get rid of this. Let's copy, and then so now they need to communicate with each other over the internet. Oh, let's have this. Okay, now, so there are possible things that may work, right? Now, internet has various communication devices that break data into multiple electronic packets, and finally, what is going to happen is when Bob sends it, this is going to get broken down into different packets, and then when I come here, I'm going to reassemble those packets and get the data. Now, so for example, this person is A and this person is B. This person A creates a web page. He lists the files that Bob needs to download. Against each of the files, he shows CR32 values of the files. B is going to download these files, compute CRC32, and check whether if if he has got the same files as A sent. Now, this CRC is basically derived from data to ensure that this is basically what we mean by message consistency, right? That means whatever A sent, B got the same thing. Now, okay. Now, it determines the consistency of data. Now, in an electronic summary of the data, also known as the digest, then you have something called as cryptography digest. Now, cryptography digest should follow certain properties, right? Basically, one should not be able to guess the message from the digest. If a message M1 led to a digest D1, finding a message D2, M2 will have the same digest should be computationally intractable. Okay, so then he's saying how to. Now, the electronic summary of data is also called as a digest. Now, from this digest, no one should be able to guess what the message is. If there is any minute changes to the message, the some computationally algorithm, some computation should be performed so that you get an output which does not match, and then a small change in the message will result in the smaller will produce a different digest. Now, using cryptographic hash functions, we can fulfill the digest properties. You can use some cryptographic hash functions as well. Okay, now protection. Now let's see about protection, right? What do you mean by protection? Now, if there is any information protection achieved with message consent, now here, okay, so this is basically how our message is going to be transmitted, right? You're going to do a CRC at this end. You're going to do a CRC or a cyclic check at this end. Basically, to make sure that what was sent has been received, and so in this entire mechanism, there is no way of protection, right? There is no protection happening. What if a person is sitting in between the network? He can listen to the traffic, right? This is nothing but called as eavesdropping. When a person sits in the between the network and is able to understand or read your traffic. So what if the person is present here? So instead of you reaching the server or you reaching the person B, you reach this server, but you think you have reached already the server. So this is again something called as a man in a middle attack, right? Or very commonly known as MIT, MIM. So, however, there is partial protection against a message tampering attack, right? In the preceding example, if the mail read changes the message only, okay, so what is going to happen is, although we are going to, so Bob will come, sorry, the B will come to know the message changes only if A will change the message. That is what is trying to do, because A is going to produce the cyclic check. Suppose if a person B who is sitting in between reads the messages, and then again B does not know what was sent, right? So only at the sender and the receiver end can we check whether the anything has occurred or not. That means if some there is distortion here, then this also will be, then we will produce a different code, right? But there is no way of actually checking whether um, was it the original message that he transferred. So this is basically called as hence why we need, hence is the reason we need protection, right? um, so I mean, even if a person is sitting in between, if he changes the message, then only the CRC will change, right? So let me see. Yeah, I got what he's trying to say now. So basically, suppose if you have two persons, right? And these two persons are trying to communicate via the internet, right? So this is where the communication is happening. Now, in so data link layer, so the message won't be sent as a message, right? Instead, what we would be doing is we'll be dividing these messages into different packets, right? Or different packets of different size, and these different size packets will then be uh, transmitted over the network. So instead of having one single packet, you have different packets being sent out. Now, so at the data link layer, what we do is we employ a mechanism called as CRC, right? To check if there is any distortion in the message. That means, what if so what does CRC do is basically, um, so when we send a message, now this message will be converted into some form of code and then sent to the receiver, right? At the receiver end, again we will decode the message and check if the CRC matches. If the CRC is a match, then we got what was intended to transfer. Now, what if a person is sitting in between and he's listening to the traffic? Now, this person is not doing any changes to the message, but he's just listening. So, in such a case, CRC will be of no use, right? Even though it will determine that the person A has sent the proper message to person B and there is no distortion in the channel. Now, this person can listen and then replicate the message and then access some important information, right? Which the person B or the person sitting in B between should not be able to access. On similar lines, what if a what if the person is sitting in front of B? Now he can monitor, right? I mean, and what if he gets the message? Again, CRC will make sure, and he's not making any changes to the message. He's passing on to B, but all the valuable, he's able to extract all the valuable information, right? There is no protection against these two attacks, right? Hence, we need some sort of protection, right? So this is basically where we introduce something called as cryptography, right? Now, cryptography, you can define it into two types, right? Symmetric cryptography and asymmetric. So let's see symmetric cryptography. Now, eavesdropping and man-made in the middle can access the whole communication, right? This is a breach of privacy. Let us decide to use the following scheme to communicate. So let us see. Now, what we do is basically instead of sending the original message, okay, so A and B have never met. There are some nodes on the internet. There exists only one scheme that everyone uses on the internet, but it also needs a key that establishes the trust between A and B. A and B can never meet. Let us try to understand each. Let's just try to understand each step and find out the limitations they pose. Okay, so what if we do is okay. So let's develop our method. So how to add protection. So one simple solution to adding protection is basically what you do is uh, uh, this is A and this is B. Now what we do is we agree on a scheme or a um, on a mechanism for some sort of scrambling, right? Now okay. So yeah, let's develop some sort of mechanism, right? So first is basically um, mm, okay. Um, okay. So there are some nodes on the internet. They exist only one scheme that everyone uses on the internet, but it needs a key that establishes the trust. So what we do is basically you kind of put in a key over here, and this is you generate a key using a mechanism that is available for all. Okay, and okay, so first is basically you agree on some mechanism using which you are going to scramble, and everyone knows it. The second possible way is basically a shared C. A shared secret must be established between both of them using an output. So you use a secret mechanism that is known only to A and B. Now this kind of acts. This kind of can become the problem. Now the other is the persons on the link, like who are eavesdropping, can see the messages, but they cannot able to understand or cipher the text, while the original message is a plain text. Now B uses the key that is given by A, and only A has that access to that key. No one else has access to the key. So now in previous methods we used the word scramble in a more generic sense. If you have the data that generates an output of n bits, every bit pattern is equally likely unless you have the key with you. In perfect cryptography world, all values are possible. Now cryptography functions have a randomization property. If you want to reverse the results of cryptography, like decrypt or verify the cipher, you will need the key. That is, they are called as one-way functions. In the presence of the key, computations can be carried out and the cipher can be... What is he trying to say? Hmm. Let's understand how this symmetric key or symmetric cryptography works. Okay, so let's see first how symmetric key or symmetric cryptography works. So basically, what we are going to do is in symmetric cryptography is, if this is the sender and the receiver, okay, what you are going to do is at this sender, let's have it this way, and what I'm going to do is at the sender end, I'm going to decrypt or into some other message, and I'm going to send this to the receiver. Another, so oh no, I'm not. Okay, what I'm going to do, I'm going to convert the message into an encrypted format, and I'm going to generate a key. Now what the key is going to do is, um, so using the key when given to the encryption, you can get the original message. Now at the receiver end, what I'm going to do is I need to decrypt the coming message, right? So what I'm going to do at the receiver is I'm going to need the encryption as well as the key at the receiver end, so that I can get the original message that was being transmitted. Now, what do is basically, um, now what I need is, along with the message, I need this key also to be sent to the receiver, right? Because if I don't have the key, I won't be able to get the message back. Now, uh, so to get the message back, I need the key. So they are called as one-way functions, right? In the presence of the keys, computations can be carried on, ciphertext can be obtained. The absence, the cipher is all random words, right? Bigger the cipher, harder is to guess the plain text from the cipher. Now, since this cryptography has a randomizing effect, we are going to use a random algorithm. And it's only the algorithm that are cryptographically secured and are, so basically, we are going to use a function that is going to be very secure. Okay, so this is how it is going to work. So first is basically, what they do is, first is both of them encrypt the message. Then once the message has been encrypted, so at the sender's side, I encrypt it, and then I generate a key and I send to the receiver. Now, uh, however, it needs this key to be present as well. Now, encryption, there are a few misconceptions, right? An encryption operation generates the same number. So, what is going to do is, uh, so like after encrypting, like what will be the size of the data? But if you have that, then you can try to guess the message, right? So basically, we are going to do some sort of randomness. So it may add or may may remove some. It may add some extra additional messages. So basically, the message that we sent will be much bigger than the original message. Now, the other thing misconception that people have is the encryption and the decryption. So other misconception is, um, so if I use some algorithm to generate this encrypted message, and if I use another algorithm to decrypt the message, now, mm, mm, okay, what if these two mechanisms are methods are not related to each other, right? Like what I mean to say is, what if this encryption algorithm is something else and this decrypting algorithm is something else? Now, will the key, yeah, even though the key is being sent, will it still be able to decipher my message? No. The algorithm also needs to be the same, right? If the even though you have the key, but you are using a different type of algorithm to decrypt and a different one to encrypt, you still will be able to get the data. Okay. Okay. Now then we have something called as signing, right? Now what is signing? A signature to be valid should only have the following properties. It should be authentic. The signature should convince the document's recipient and the signer deliberately signed the document. The signature is unforgeable, right? No one can forge it. So signature is not reusable. The signed document cannot be altered. Signature can be not be repudiated, right? That means copy cannot be made. No one can copy this. Okay, for example, if you do a document signing infrastructure, right? So how will that work? Okay, let me. Okay, so what are we? So first way of achieving asymmetric is basically you do encryption and decryption, right? So there is one more ways. What you do is you do signing of the document. Now what you do is So here I'm encrypting and decrypting, right? So what if I'm signing the document? What if I'm using a sign as an indicator? So basically, when we are using as a digital signature, uh, like it should have the following properties, right? First is authentic. It should be unforgeable, cannot be reusable, it cannot be unalterable, and the signature cannot be reproduced, right? It cannot be copied. Okay, so now what I'm going to do this is basically uh, so the way this is going to work is, what if we use digital signatures in alteration to encryption or decryption? So let's see that. So this is my these are the two people you want to communicate, right? So this is let's say this is person A and let's say this is person B. What if now instead of doing encryption, what if we use something called as a signature, right? So what we do is, now here instead of sending it to the receiver, we have an intermediary step called as verify. Okay, this is how decision. Okay, so uh, now A is going to send the message directly to this verification company, as well as what it is going to do is it is going to send its signature. So you're going to send the signature uh, to the verification company as well. Now, so when we send the signature, along with the signature, I'm going to send the key as well. So here the key is going to come, and when the message, the key is going to come. So what I'm going to do is, so in this, I'm going to verify if the signature was authentic or not, right? Yeah. So what are we going to do is, you are going to use the message and the key to generate an hash, right? So basically, you're going to create a code over here. So this is the message plus key, and then here, at the at the signing end, what I'm going to do is, with the help of the signature and key, I'm to check if it is the intended user who is sending the message or not. Okay. uh, okay, so there are two problems that we have here, right? Um so first one was no one should be able to read our message. That is overcome by using encryption, decryption. And second is to make sure that we are sending it to the intended user, right? So that is that is ensuring using, so that is what we are using digital signatures, I guess. Yeah, so there are basically two possible problems that we are trying to solve. First is basically eavesdropping, wherein a person can get to know what the message is. So that is basically using encryption, right? And signatures is basically for man in the middle, making sure that um, the information is for the intended user. So so now how are we going to encrypt is basically okay. Okay, okay. Yeah, so there are potential two problems in any network system, right? First is basically a man in the middle attack, where a person sitting in between can no no. So first is basically eavesdropping. Basically, a person sitting in between can access the data, right? So to overcome that, we use encryption. Now, how that encryption is taking place, like whether the we'll do that using a key, right? So whether we are sending the key to both the sender and the receiver is something a part of symmetric cryptography. And again, digital signals is basically used to check if the intended person to which the data should be transferred to, whether he is the intended person or not. So that again, the way that we are going to achieve this is using keys, and whether the keys are going both to the sender or receiver or not is basically a part of symmetric cryptography. So we are not dealing with that right now. Oh, so yeah, we are dealing with the yeah, we are basically dealing with symmetric cryptography, which basically means the key will be sent to both of them. Oh, so and we haven't talked about the different algorithm, right? How the algorithm or how that encryption algorithm is going to work. Hmm. Okay. So this is basically signing, right? So here we are basically signing, like we're not introducing digital signature. That is something else. Okay, so yeah, I guess that is all for this lecture. I'll see you guys in the next one. Till that time, take care. Bye bye.